Hello everyone. Have you ever wondered about the whys and the wherefores of elementary particles, bosons, fermions, and how they are different from our everyday classical particles? I bet you wouldn't have been able to make out who's who amongst identical twins the first time you met them. But slowly your brain keeps storing attributes, the little differences in the way the hair is done, the clothing choice, and so on. And then you can distinguish. For classical particles, the hairs are detectable. The trouble begins with subatomic particles. You are not allowed to probe those tiny differences, can't even get close to look at them. There is the uncertainty that is built in. So, any form of labeling or trajectory following is a strict no in quantum mechanics. We just assume those particles to be identical. No one's ever found two types of electrons. Look at this then. It is impossible to distinguish which particle emerged on which side after a scattering event like this. You can't probe what happened when they got close. Was it this or this? Similarly, which four of the whole nucleon bunch emerged in an alpha particle decay? I hope you got the idea. Now, the trouble is, how on earth do we describe their collective behavior if we can't even make out one from the other? To resolve this, let us begin with an analogy. I am sure you must have come across movies involving identical twins. The usual premise is that they split at birth, grow up at different places, and meet later in life. Let us say the famous German Lotte Lisa story or Golmaal movie in Hindi, and then they swap places. Now, physicists like to tell stories too, stories of how the world we live in works. Imagine this story: two identical particles A and its twin B in states 1 and 2 respectively exchange places, that is quantum states. Now, remember that this wave function describes its state completely with spin and everything else in. From an observer perspective, that is you, the particle exchange should not be noticeable because they are identical. What this means is that any quantum observable must still possess the same set of eigenvalues, that is, experiments must give the same results. Let us dig into this exchange degeneracy business further. When you perform the permutation or flip or exchange operation on the two particles, the maximum you would expect to happen is the appearance of an overall phase factor. Turns out these overall phase factors are not important, they do not affect the eigenvalues. What happens when you do another flip? It is not magic that this state must be the same as our original state. Now, this can happen in only two ways: when a single flip either keeps the state the same or when it reverses the sign, that is, the overall phase factor is -1. So, the net wave function is either a sum or a difference of the possible permutations of the states. Actually, a careful look will tell you that instead of just adding and subtracting, any arbitrary linear superposition of the two permuted states should lead to an identical set of eigenvalues for the observables as the one we started out with. Either nature chose the extremes of symmetry or we have more complicated machinery than required here, but the mathematical annoyance is avoided nonetheless. The particles that are symmetrical under exchange are called bosons, and the antisymmetrical ones, the minus ones, are called fermions. But let us look at their properties. Going back to the scattering event again, we let the two scattered states come closer and closer until they coincide. In other words, we examine what the particles do when squeezed into the same quantum state. The fermionic wave function vanishes when 1 equal to 2. Isn't there an exclusion principle like that somewhere? The bosonic state on the other hand comes out intact. Now, let us list all the possible states then. From the exclusion principle, the fermions can't exist in the same state. In 2 out of the 3 bosonic states, they appear together. Now, there is no superposition principle governing the states of classical particles. So, all the product states appear independently, and in half of them they are together. So, to sum up, fermions do not see eye to eye, bosons love to live together, and classical particles do not care. How do we humans behave? Fermionic, bosonic, or a bit like both? In terms of attraction of having a house right at the center of the city, we behave like fermions and band out into a series of houses because we can't all be living under the same roof. But under the right conditions, we all condense into a stadium or a rock concert, behaving like bosons. Us crazy humans. See you again.